Okay, last time we finished the lecture by talking about how to solve the field within a triangle when we have a bigger problem. So we may have a problem that is more complex. We cannot find a trial function that will solve the solution for the entire problem domain, the entire subdomain. So in order to find the solution, we could break down the problem into multiple triangles. So in this example, we broke it down into 6 triangles. And then if we look at one of these triangles, we could say that it is it has 3 known values at the 3 points. Okay. Now, if we have 3 known values at the 3 points, which could be called nodes, these points, then then we could say that the field within the triangle is given by a linear trial function given by 11 here, which we wrote out last time. So 11 has terms of x and y coordinates, and in this trial function we have 3 unknowns: a1, a2, and a3. Okay. Now, if we substitute in the trial function xi and yi, then that will give us equation 8. Okay. Now, 8 is the value at xi here, at this node. Similarly, if we substitute in xj, yj, and xk, yk, that should give us the value, magnetic vector potential value, at aj and ak. Now we're doing this in terms of magnetic vector potential, and it's a 2D problem, so it would be in terms of az, a subscript z, but I'm just going to write this in terms of a. I'm not going to put the subscript z in order to simplify the notation, but just keep that in mind. Now for this one triangle we're looking at, we would have 3 equations, and we have 3 unknowns a1, a2, and a3. So then we could rewrite 8 to 10 in a matrix form, which is shown by 11. So in 11 we have we have it written in terms of the knowns on the left side. So we need to solve this. So we need to take the inverse of this matrix. So one way to do that is to use one way to determine the to evaluate the unknowns is to use Kramer's theory, Kramer's rule, and that will allow us to figure out what a1, a2, and a3 is. So I'm gonna use Kramer's rule to evaluate the 3 unknowns. And I'm not going to talk about the theory behind Kramer's rule. You can look that up, but I'm going to use that to evaluate. And so in order to use Kramer's rule, we have to evaluate a number of determinants. So we have 3 equations with 3 unknowns. One way to solve for the 3 unknowns is to use Kramer's rule. Okay? Kramer's rule uses determinants to solve systems of linear equations. So now if we define 2 delta is equal to 1 xi, yi, 1 xj, yj, 1 xk, yk, okay? And I'll call that 13. Now we can also define delta 1 as equal to AI xi yi aj xj yj ak xk yk, and this is the determinant, and then delta 2 is equal to 1 ai yi 1 aj yj 1 ak yk, and then lastly delta 3 is equal to 1 xi ai 1 xj aj 1 xk ak. Right? So with those four definitions, then what Kramer's rule says is that the solution to the unknowns A1, A2 and A3 can be found by evaluating A1 as delta 1 over 2 delta, and we can evaluate A2 by solving delta 2 over 2 delta, and we can solve A3 by evaluating delta 3 over 2 delta. Okay, so let's do that, and the reason I need to write this out is that it's important for evaluating the trial function. So we need to get an explicit solution. So let's do that. It's a bit laborious, but it's important to see how the finite element works. So now I'm going to leave this term up here for later, and I'll erase this. Okay. So now if we evaluate A1, so then we need to find the determinant delta 1. So delta 1 is shown here. So in order to evaluate this, I'm going to keep the AI, AJ and AK on the outside. And when you evaluate a determinant, there's a sign rules for the first term that are like this. So if we go down this column here and knock out the top row, then the first one is going to be a plus, then the next term will be a minus, and the third term will be a plus. So let's evaluate this. So the first term is with AI, so we can write out AI, and then we have to evaluate the determinant xj, yj, xk, yk, and then second term down is a minus, so it's going to be minus aj, xi, yi, xk, yk, and then the third term ak is going to be xi, yi, xj, yj, like that, and then divide that by 2 delta. Now it turns out that the 2 delta, if you look at the 2 delta, there's no magnetic vector potential terms. It's just coordinates. So if we evaluate this, it turns out that this is equal to 2 times the area of the triangle. So I'm not going to do that here, but you can check that. So we can show that so it can be shown that 2 delta is 2 times area of the triangle, and then then we don't have to evaluate the denominator. So the numerator though writing that out, it's going to be AI, and now we take the cross product xj_yk minus xk_yj. So we have xj_yk minus xk_yj plus aj xk_yi. Now here it's a minus here, and so I'm gonna and so if xi yk minus yi xk, that those two minuses cancel and you get a plus. So I'm writing it, I'm rearranging it. So we have a plus here. So we have xk_yi minus xi yk plus ak is equal to xi yj minus xj yi, like that. And that's all times 1/2 delta. Now now we're going to write this out a few times. So in order to simplify it down, I'm just going to reduce the notation, and I'm going to call this pi, this pj, and then this third term pk. Okay? So when I do that, then we have ai pi plus aj pj plus ak pk, like that, and that's multiplied by 1/2 delta, and that is equation 14. Okay, so that gives us the unknown A1 and solves for it in terms of the magnetic vector potentials and also the coordinate positions. So that's the first term. Now we can evaluate the next terms. And so then, where is that? So A2. No, let me erase this. So A2 is equal to, we need to evaluate 1 AI yi, 1 aj yj, 1 ak yk, multiply that 1/2 delta. So now this is the second term. Now I want to keep the ai, aj and ak at the front, so then in order to evaluate that, it's going to be a minus plus minus in the front of the determinant when I evaluate. So the first one, knocking out the row and column, second row, first row, second column, we get that A2 is equal to minus AI 1 yj 1 yk plus aj 1 yi 1 yk minus ak, which is 1. Third one, we knock out the bottom row and the second column, so we get 1 yi 1 yj. Right, I think that's right. And that's all multiplied by 1/2 delta. Now we can then keep going. So these ones are easier because there's no x. So it's going to be yk minus yj. There's a sign in the front, so sign changes. So we get yj minus yk plus aj yk minus yi minus ak yj minus yi. and that's 1 over 2 delta. Now we can collect terms again, and so that will be AI QI plus AJ QJ plus AK QK. Okay, where these are the coordinates. And then lastly, so that's A2 solved for the magnetic vector potentials and the coordinate positions. And then lastly, A3 can be evaluated. So that's 1 over 2 delta, and we have to evaluate the determinant 1 xi AI, 1 xj aj, 1 xk ak. So when we do that, we get out AI. Let me just write out the solution here. So AI will, again, we'll keep the AI, AJ, and AK in the middle, at the beginning, and so we'll cancel out. So we'll get cancel out the row in the first column. That will give us xk minus xj. So we get AI xk minus xj plus aj xi minus xk, and I've changed the sign here, plus ak xj minus xi. And so then, now we can simplify this last term down to be AI Ri plus aj Rj plus Rk Ak times Rk times 1 over 2 delta. And that's equation 16, and this was a 15 here. This is A2. So the Ri is equal to xk xj, and Rj is equal to xi minus xk, and so on. Okay, so now we have determined what A3, A2, and A1 are, and then our trial function is given by 11. So we can substitute in the unknowns now, A1, A2, A3, into 11, and we'll get out a solution to the trial function, which will, and the solution of the trial function will be only in terms of the magnetic vector potentials plus the coordinates at the nodes of the triangle. Okay, so let's do that. So substitute 14, 15, 16 into 11 gives, so we do that, we get A hat is equal to, so the first term, which is AI PI plus AJ PJ plus AK PK. That's the first term, plus the second term AI QI, this is A2, plus AJ QJ plus AK QK, and that's times by X, plus the third term, which is, this is now A3, so we have AI Ri plus J Rj plus AK Rk, and that's multiplied by Y. and we times that by 1 over 2 delta, and we'll call that equation 17. Now that gives us now the solution of the trial function, where we have the coordinates x and y. Now let's just rearrange this, and so let me write that in terms of x and y. Okay, so let's now rearrange this in terms of the AI, AJ, and AK. So rearrange. So if we rearrange it, we can rewrite the trial function in terms of the magnetic potential values. So we have A xy is equal to AI. So collecting terms for AI, we have PI plus QIX plus RIY, and then we have AJ, which is PJ plus QJX plus RJY plus AK, which equaled PK plus QKX plus RKY. And that's all multiplied by 1 over 2 delta, like that. Now if we look at this, we can, now we've got the AI, right? That's the known value at that node, that triangle point. We've got the triangle with the three nodes, AI, AJ, and AK. So this is the known value at AI, and that's written in terms of a function which has a coordinate x and y in it, and similarly for AJ and AK. So we could now rewrite again, further simplifying down the trial function. So let's now write that trial function in terms of 3 functions. So the AI would just be some number, some value at that point, and AJ and AK would just be some number given at that value, at those 3 nodes. So we could write out that A hat is equal to AI NI X Y plus AJ NJ XY plus AK NK XY, like that, where the NI is equal to the PI QI X RIY. Okay, so we have NI is equal to one over 2 delta, and we've got the 1 over 2 delta here, don't forget that. 1 over 2 delta PI plus QI X plus RIY. Then NJ is equal to 1 over 2 delta PJ plus QJX plus RJY, and NK is equal to 1 over 2 delta PK plus QKX plus RKY. That's 21. So these three functions here, if you look back at when we were looking at other trial functions, you could see some similarity. These three functions here are the trial functions. Sorry, not the trial functions. Gosh, these three are the basis functions. The basis functions. A is the trial function, and so we have three basis functions. So these are the basis functions. In COMSOL they're called test functions. So these are the basis functions. Now, this is our solution to the trial function. This is our solution trial function. So this equation here needs to satisfy the field everywhere within the triangle, but it also must satisfy the values at the nodes. So at AI, AJ, and AK. So if we were to put in the coordinates for xi, yi, we better get out ai, because that's what is the value at that point. If we put the coordinates in for xj, yj, we better get out aj for the field value, and similarly for ak. So let's just check to make sure that this trial function satisfies the boundary conditions. Okay, so if we can do that by substituting xi and yi into here, and we should get out ai as our answer. Okay, so let's spend a little bit of time just double checking this. So the basis functions must give correct nodal potential values. So for example, so if we have x, y is equal to xi, yi, what will we get? So let's substitute in for the, let's substitute xi, yi into the basis functions and see what we get. So if we write now, we need to write out the basis function completely. So to remember that pi, qi, and ri, those three terms are written in terms of coordinate positions. So let's just expand that out again now. So ni is equal to 1 over 2 delta times, I'm going to run out of space here. I'm going to keep this because we're going to use that again. So ni is equal to 1 over 2 delta x j yk minus xk yj plus yj minus ykx, and so this first term here is pi, the second term here is qi, and then the third term, which I'm going to write now, which is xk minus xj y. So this is the third term here, which is ri. Okay, so now we're going to substitute xi, yi into this basis function. So doing so, we get that we have ni xi yi is equal to 1 over 2 delta xj yk minus xk yi plus yj minus yk xi plus xk minus xj yi. Now it turns out that if you compare that with the equation for the area of a triangle, that this and these terms in the square brackets is equal to 2 times the area of the triangle. So I'm not going to prove that here. I'll let you check that. So this then, if this in the square brackets is equal to the area of the triangle, 2 times the area of a triangle, then this becomes a big 1, which is good. So let's then evaluate nj, see what we get. So again, what we're trying to do here is check that if we substitute in xi, yi into the trial function, we should get out just ai, because that's the value at xi, yi. So then this one has been checked. We got out ni being 1. So that will give us ai. Now we need to make sure that these two terms will be 0 at xi, yi. So in order to satisfy the nodal point. So let's check for nj. So nj is given by 20, and we can expand out pj, qj, and rj. So let's just take the time to do that. So nj is equal to 1 over 2 delta xk yi minus xi yk plus yk minus yix. So this here is pj, this here is qj, plus xi minus xk y, and this last term here is rj. Okay, so now let's substitute. This is the basis function when I expanded it out. Now let's substitute xi and yi in and see what we get. So nj xi yi. Okay. So the first term doesn't change. So we have xk yi minus xi yk plus yk minus yi xi plus xi minus xk yi, right? Now if we look here, we've got xk yi, and now we've got minus xk yi, so that term cancels, and then the second to last term here is xi times yi, and then we have minus xi yi, so that cancels. And then lastly we have minus xi yk, and then here we have plus yk xi. So this term cancels too. So it all cancels out and we get a nice 0, which is great. So this term evaluates to 0 when we substitute xi and yi in. And similarly, you can check that if you substitute in for the you substitute in xi, yi for nk, you also get out 0. So if we do that, so we got nk is equal to xi yi, and we put that in, we'll end up finding it's equal to 0 too. Okay. So in summary, then when we substitute in xi yi into our trial function, we get this being 1, this being 0, and this being 0, so we end up getting ai, which we should. If we didn't, we'd be in trouble. And So then we should also, if we substitute xj, yj in to the trial function, we better get out aj, and similarly for ak, we better get out. So if we substitute xk, yk in, we better get out ak. So then we'll, I've shown that for xi, yi, the trial function is satisfied, and it is similarly the case for xj and yj, and also for k. Okay. So I'll stop there, and then we'll carry on in a minute.